Good afternoon. We'll continue with the discussion of sequential machines. We are taking a somewhat different view of sequential machines than the traditional view, which you will find in textbooks and other courses. So here we always think of sequential machine in terms of an object and its functionality. You know, you can manipulate the methods of an object, and that's the only thing you can do. And we'll see today how we can use all these ideas to connect various sequential machines together to build bigger and bigger sequential machines. So just a quick preview of what you have seen, but let's make sure all of us are on the same page. There are three types of methods a module can have. This one is simply the value method or read-only methods. These methods let you look at the state elements inside a module, right? So if you, it doesn't affect the state, but you can read the state of through a value method. You already saw two examples of it. Mod4 counter dot read, right? That told you what the current value of the counter was. You could also read a GCD busy, right? That GCD is currently busy, GCD module, or GCD is ready with the results, and so on. The other kind of method is an action method, which is designed to actually affect the state of the module. And the examples of that was when you said mod4 counter dot inc, that means incremented. You're definitely affecting the state, which is internal. You may not know exactly how the state is represented, but the point is that whenever you execute this method, it's going to have some change in state inside it, or GCD start. Now, the thing to understand is whenever you say an action method, you have to think of it. Read method is just, value method is simply you're reading something coming off the module. But for action to take place, you have to press a button, right? So I will always be showing these things as enable lines, or I'll draw them in red almost exclusively. So every action method has a ready line associated with it. And the value of the ready line has to be true before the method effect takes place. Okay. And the last kind is a combination of the two. It's called action value method. So it affects the state of the module as well as it returns a value, you know, from the module. So you're doing both. You're affecting the state as well as you're seeing something coming out of the state of the thing, and it's returning a value of type T here. So that's why it's written action value of type T. So example of this was GCD get result. You're going to get some result from the GCD, but at the same time you're affecting the state of GCD in the following sense, that this result has been consumed now. You can go and do the next thing. Because if you don't have this kind of a thing, then you may overwrite whatever was inside GCD. A circuit for action value method also has an enable wire associated with it. In other words, the effect, this method takes effect only if the value of the incoming enable signal is true. And any of these methods can have input parameters, right? So you may, for example, when we compute a GCD, you know, we are supplying arguments X and Y, whose GCD is to be computed. So input parameters are permissible in all three kinds of methods. Now let's look at it from the other side. Until now I was telling you about the definition. This is the interface of the method. How do we use them? Right? So what is the syntax and what is the idea behind using them? So a value method, essentially a call to value method, is simply an expression. So I can say, for example, counter value equals mod4 counter dot read. So from now on, this value will be called counter value. And you may recall what let was. Let will automatically figure out what the type of this is. So it'll go and look at the definition of module 4 counter, or it'll look at the definition of counter value, etc. Somehow it will figure out what should be the type of this value that is coming out. Similarly, I could have said bool is GCD busy, which is essentially the signal busy coming out of the GCD module. Okay, so always think of value method as simply an expression, and you know by now that expression you can always name it. You can assign it to variable t, and you use t from there onwards. All right, action methods. So action methods don't return anything, but so they're like a statement. You're saying something, you're writing it down, and some effect will take place. So you have modulo counter dot inc, parenthesis, semicolon after that. So that's saying do this, right? Execute it, increment it, the thing. So in some sense, whenever this thing executes, that red signal will be made true at that point. Okay, or you can look at it the other way, that red signal has to be true before this method call will have an effect. You can do GCD start, you can give it some values, and it will start the thing. Now when you have action value method, then you use, instead of equal sign, you use a left arrow. And this is often a stumbling block for many people. They're saying, why left arrow? What's wrong with using equal sign? Why can't I write result GCD equals GCD dot get result? And this is a subtlety you have to understand, and you cannot make mistakes, syntactic mistakes, otherwise lots of things will go wrong. So suppose we wrote this. Suppose I wrote equals instead of left arrow. What is the type of the right hand side? What is the type of the right hand side? What is the type of GCD dot get result? It's an action method, right? And what do you want from it on the left hand side? You don't want an action method, you want a value of type t, right? So these are two different beasts altogether. You can write this, right? And then if you will have to use get result or GCD as an action method, and that's not what our intent was. Our intent was we wanted to actually use the value that is being returned, and therefore you have to write the left arrow sign over there. So just remember, any time you use equal sign in this language, it's always just a naming thing, right? The thing on the right hand side has been given a name, which name of your choice, and by definition the types on both sides have to be the same. If you have some expression, or you have whatever you have, and if you say t equals this, so the type of t and the type of right hand side are always the same. Left arrow is the thing that is changing the type. It's saying right hand side is action value method, but the left hand side is actually a value of type t. Okay, you'll get used to this, but I'm just warning you that remember, anytime you use action value, and also at this point you may notice that left arrow is slightly overloaded, because we had also used left arrow for instantiating modules, right? So that's another thing to remember. Okay, let's go over the GCD implementation which we rushed through at the end of the last lecture. So this is the interface of GCD. We have an action start. We'll give it two values and we expect it to get going. And we have action value, result, you get result, return something, affects the state. And we have two flags, a busy flag and a ready flag. Ready means result is ready, busy means that the input is. You can't do it because the module is already busy doing something. That's the high level idea. And now let's see if we can write an implementation for it. So first thing to understand is the moment, how do I fill this body, right? So I'm writing a module, and it's a convention, though you can name it whatever you want. I'm calling it make GCD. I want you to make me a module of this type GCD. And the very first thing I do is I instantiate before that, and because the type is GCD, I have to support all the four methods. and therefore I have written down the headings of those methods over here. So you see there is a start action method start, action value method get result, bool method busy, and bool method ready. So we have to write down the definition of all these four methods in order to define an implementation of a module. The next thing we always focus on is what are the state elements, right? What is the internal state of this? And you can see that we need at least two registers X and Y to hold the values of the two variables that will be repeatedly updated as we compute GCD of this thing. And then we have a separate flag called busy flag, which tells me whether the GCD, whether this module is busy computing a GCD or it's not. And you'll see that it's initialized to false. So initially it's not busy, right? And similarly, the registers are initialized to 0. Both of them have value, each one of them has value 0 in it. Okay, given all this, let's see if you can write down the start method. So what does start method do? What does start do? It has two arguments, right? And the arguments are A and B. What should we do with these? Put them in internal registers, and internal registers are X and Y. When can you do this? You should do this when the GCD is not already busy, right? So that's what you will see here, that X gets A, Y gets B, and busy flag becomes true. Does everybody understand the start method? Now notice I didn't do any check whether the method was busy or not. So this is a burden now on the user. Whosoever is calling this method from outside better have a predicate which says if busy, if not busy, then start. It's a separate check you have to perform from outside, not very uncommon in what you will do in a software language, right? You will say if a stack is not full, then you will push something on it, right? Sometimes the language itself will insert the checks into such an operation in software. Okay, so start, I just took the input values A and B and put them in internal registers X and Y and marked myself as busy. Now I'm computing. What is get result? So whenever get result is, you actually pick up the result, at that time we will declare that the module is no longer busy because you have picked up the result, and we can take the next thing coming into it. But we also have to know, has the model actually finished computing? And that, for that, you have to have a separate check. Again, it's not being performed in this method. Does anybody know when the module is actually, when the result is ready? I did not show you the GCD algorithm. Does anybody remember when does it terminate? When the Y value was 0. If you reach that far, that means you had found the GCD. So that's what you have in the GCD ready flag, which is result ready, I should say, and that just says X equals 0. If X equals 0, then it is ready to be executed. And a busy flag is simply the value of the busy flag. So initially it's not busy because that's how we initialized it. But after we have started it, see, we changed its state to mark it busy. To mark it true. All right. Now, visiting again the action value method, two things are happening. One is I'm saying I'm no longer busy. So that's a change in state. Inside state is changing. And the second thing I'm saying is I'm returning a value. What is the value being returned? Y, because Y is the result of this computation. Return Y. So that's what these things are. Okay, so I have given you the definition of 4 methods in this, which is required by the interface. But we still haven't computed the GCD. So where is the soul of GCD? How do we actually compute it? And that's the algorithm here. So there is a rule. I'm introducing a new kind of a thing called rule. Its name is GCD. And let's see if this code makes sense. What does the rule say? If it says if x is greater than or equal to y, then you do a subtraction. Then you say x gets x minus y, right? And if it is not, then what do? Swap them. You say x gets sorry. Yes, x gets y and y gets x in this. And you don't want to go below 0, so that's the check that is happening there. If x is not equal to 0, then you keep doing this. Does everybody understand that this description here of a rule corresponds to exactly the algorithm we showed you? Right? You have 2 numbers, x and y. If this is bigger and this is smaller, you subtract it and update the state. If this turns out to be smaller than this, then you swap them. Right? That's what is captured here. And then you stop if y becomes 0. Yes?
So is this rule just constantly running as long as there's any value?
That's how you should think about it. That a rule is always trying to execute. We'll discover very quickly why it may not, but our mental model is if I write a rule, it's always trying to execute. Yes?
When you swap the variables, you said like x equal to y and then you said y equal to x.
Yes.
Not equal, or like
I'll explain that in just a second. Okay. I mean, that's what we want, right? According to the algorithm, we want to swap x and y. Now, why does this syntax work like that? I'll explain in a second. All right. So this is the question that was just asked, that rule GCD executes repeatedly until x becomes 0. Yes?
How does it know when to stop when x is 0? Isn't the first condition that x is 0?
I think it doesn't quite stop, but what you will notice is there is no state change after that.
So it'll realize that you're going to
No, you don't even have to. In hardware, these things are a little bit funny. It doesn't have to stop. If it executes, what will happen? There will be no change in the value of any of the variables.
But it doesn't like waste computational power or anything?
So that's a very good question. We can get into the power discussion, but generally in hardware, power is much more related to how much signals change. So if signals are not changing, there is no power. I mean, very little power is being used. But we can write it differently so that even that won't happen. But the way it is written is, after x becomes 0, actually the rule still executes. But when it executes, there is no change in state. It remains whatever state you had. Good question. Now, as I said, there is some burden on the user of this module. From the outside, you have to make sure you don't call start if the module is busy. You don't try to read the results unless the results are ready, right? So that part is not being enforced by this code. I'm relying on some convention. This is not very different from that what will happen in many software languages. We say don't step out of bounds, do a check. You may do the check explicitly. In some languages the check may happen implicitly. But there is a burden on the user to use this module correctly. Okay, let's re-examine the rule again. So this is the same rule that you saw on the previous slide. A module may contain one or many rules in it. Okay, a rule has a name. The name of this rule is GCD. Okay, a rule is a collection of actions. By definition, you have nothing but actions, right? And you just write lots of actions and you collectively think of it as a rule. And each action itself is a method in it. All actions in a rule execute in parallel. And we have to understand exactly what that means. But don't think of them executing sequentially. They all execute at the same time. The right way to think about this is you always read the current values of the variables and at the end of the rule you update all the variables in one go. So let's focus on this, which is the question that was raised earlier. What is the meaning of this, right? And one way to think about this is that I read, look at these t's that I annotated these variables with. So right hand side you're reading the current value at time t, and the left hand side is telling you what will be the value at time t plus 1. And when you think of it like this, it will act as a swap, because you're reading x and y currently, and then in one step simultaneously you will update them. Okay, so that's why it acts as a swap. Okay, so that was the point, and again this you have to be aware of because this is different from software. Yes?
So what would happen if you used the normal equal sign?
Sorry?
What would happen if you had a normal equal sign?
Normal equal sign. Oh, instead of left arrow, hell will break loose. Is that the question? So tell me what will happen. Suppose it was an equal sign. Suppose you said x equals y. What is the meaning of equal sign? It's just saying that whatever, you had a register named y, and from now on you want to call it x. It doesn't say anything about values being transferred, because it represents a register. I mean, if I was to write it explicitly, the right hand side should say y dot underscore read, right? I mean, there is an implicit read operation going on there. And the left hand side is saying x dot write. You're writing something into x. Okay, so you absolutely can't, I mean, the right syntax for this, verbose syntax for this would be something like this. You will say x dot underscore write okay, this is syntactically written as, oh sorry, okay, this is just a syntactic sugar for this. Very good. Now this is the thing which is even more important, and you cannot forget this. So whenever we execute a rule, you cannot talk of intermediate states during the execution of a rule. You have to always think in terms of what is the current state of all the variables, xt, yt, whatever variables you're reading, right? And after you have executed the rule, what is the value of all these variables? Because anytime you're doing an assignment, you're going to be changing their values. So the important thing is, you can't say, oh, what is the value after I have executed this action, or after I have executed that action, as you often do in sequential languages. Here they will all be updated simultaneously. So you do all the reading first, and at the end of the clock cycle, you will be updating all the variables in it. And this property is known as atomicity. Very, very important for defining hardware. So what we are saying is, I may be specifying 6 different register transfers in a rule. But when the rule executes, either all 6 of them execute or none of them execute. There is no partial execution of a rule. Okay. Now there is some other things you have to worry about in this. So I have written down 3 rules here, 1, 2, and 3, which are actually quite similar to each other. And what I want to make you aware of is the so-called double write errors. If there is any possibility of a double write, then the rule is illegal. Okay, so let's look at rule number 1. Is there a double write possibility in there? Yes, because x is being updated to 5 as well as 7. So this is clearly a double write. What about the second one? Anyone? Okay, why not? You're saying there is no double write here. Why? I am writing into x7 and x5 again. But either I'm writing 7 or I'm writing 5 depending upon the predicate B. No double write. There is only one such possibility when this rule executes. So there is no double write in this case. The last one is the trickiest. If B is false, there is no double write. But if B is true, then there is a double write. So we are conservative. If there is any possibility of a double write, we say rule is illegal. You can't access this. This rule will not be allowed. Now the good news for you is that BlueSpec compiler will flag a rule, so it doesn't let any double writes go through. Right? So the moment it detects a double write or a possibility of double write, it will come back and say, sorry, illegal rule, you have to change it. This helps you a lot, when you are debugging your codes. All right, so we've done enough with, not quite enough, we'll do more with GCD, but let me introduce another module which is also extremely important. It's called a FIFO, first in, first out. Now first in, first out is a extremely useful and popular data structures both in hardware and software. You will encounter it if you haven't encountered it already in all kinds of courses you take. All right, so it's often used for connecting things together. And I deliberately use the word thing because we may connect combinational circuits together, we may connect modules together, etc. But it's something that is sort of things flow in and things flow out of it. And the reason it's called a FIFO is we think of the guys who are producing as producers of a value. They enqueue something, and the other side, you consume it. So consumer of the value, it pulls it out, and it's first in, first out because you maintain the order. The dequeued values will appear in the same order in which they were enqueued. In other words, there is no shuffling of values inside FIFO. Just as a contrast, the stack that you have already seen in software is often referred to as last in, first out. Because in stack, whatever goes in last comes out first from the stack. This is the other way around. First in, first out from the circuit. So it's a useful thing to know, this data structure. Now in hardware, FIFOs are almost always fixed size. And you'll be surprised that we find even one element FIFOs extremely useful in hardware. Though we will not think explicitly whether it's one element or not, but if it's one element FIFO, that means maximum capacity of the FIFO is 1. Now it doesn't matter whether it's 1 or 10 or 100 or 2. What is important is to understand, because of finite capacity, if I try to enqueue something in the FIFO, when it's full, your enqueue will not succeed. For enqueue to succeed, FIFO has to have space, right? And same thing is true for dequeue. You cannot dequeue unless FIFO has something in it. You can't dequeue from an empty element, empty FIFO. All right, so these are the checks. You are always checking whether a FIFO is full or whether it's empty. Now let's see what kind of interface I may give it. So we have defined two Boolean flags, not full and not empty in this, and then we have enqueue values of type T in it, and we can dequeue things, and we can look at the first element in the FIFO. And if you are enqueuing values of type T, then when you do the first element of the FIFO, it's also going to be a value of type T. Now remember, when I look at the first element, it's just a read method. Doesn't affect the state of the FIFO. What affects the state of the FIFO is a dequeue operation. If you want, you could have defined a joint operation, an action value method called pop, right? That will actually dequeue as well as give you the value of it. No difference, right? You can define it like that if you want. All right, so this is the type of the FIFO in this case. All the elements of the FIFO must be the same. Now, again, just like GCD had some restrictions, the use of this FIFO has some restrictions. In other words, user has some responsibility. It should not try to enqueue anything into the FIFO unless it has space in it. And it should not try to dequeue anything from the FIFO. A consumer should not try to dequeue anything from the FIFO unless the FIFO has something in it. Okay, so these things have to be checked specially. You're always checking these flags, not full, not empty. Now, another idea you have to get used to is anytime I have a module, it's going to have an interface, and really interface is the type of the module. Interface defines the type of the module. Okay, we are ready for the implementation of this. So since it has 5 methods, I have to actually write down all these 5 methods in it. But first I have to declare the state elements in it. So I have to have a register to hold the value. It's a single element FIFO, right? So I have a data register called D, and it must be of type T if you are making a FIFO of type T. So you are instantiating a register. You're saying make me a register, and in this case we are saying it is uninitialized. Make reg U. U stands for uninitialized. We don't know the initial value. We don't care what the initial value is. All right? Now, to know whether it actually has something or not, I need a flag. I have a separate 1 bit to indicate whether this data register contains anything or not. So I'm just calling it a bool, for V here, and I initialize it to false because initially it's empty. And because it's empty, its value is irrelevant at that point. Everybody understands this type declaration. So it's a FIFO of 1 element, right? So if you had 32-bit values, then you'll have a 32-bit register, but then you need an extra bit to tell you whether the register contains anything or not. All right, so given all that, it's fairly straightforward to write down various methods for it. So let's see. Not full. Not full is? You simply return the value, not V. By the way, I could have also written it using equal signs. I could have written here not full equals not V. So this is just a different syntax, for the same thing. You can discuss it more in the recitation tomorrow. Not empty, simply saying if V is true, then obviously it's not empty. So you're returning the value of V. Now tell me what will happen when you do an enqueue. Conceptually, what should happen when you enqueue something? Assuming somebody has already checked that there was space in it. Where should the value be stored, incoming value? Anyone? Register D, right? And where should the flag should become now? True, right? So that's what you see here. The V is true and D gets V over there. And what should happen when we dequeue it? At that point, we don't care about the value. What we are most interested in, that the flag should say it is false, that we have nothing in it, right? So V is assigned false. And first just reads the value, whatever value you have in it, so it just returns D, whatever value you have in the data. But again, it's important to understand that for correct use of it, you should enqueue only when the FIFO is not full, and you should dequeue only when the FIFO is not empty. Oh yes, so we have this thing, proviso. So when I say it can hold things of any type, that's almost true. You see, in computer science, you can have such bizarre values that they may have no clear bit representation, right? So there is a notion in hardware when we say a value is bitifiable, right? It can be represented using some finite number of bits. that you have. So anytime you store things in registers, this, later on in memories, they have to be bitifiable, right? They have to be bitifiable. So we're saying, yes, any T will do as long as, provided this type T is bitifiable. And the way to say that is to say that it can be represented, type T can be represented using the number of bits TSZ, T size. I don't specify exactly what that is. As long as it's any number, that'll work. It has to be bitifiable. Don't spend too much time on it. It's just to say that there is sometimes, when you write down types, there is sometimes a little bit of a caveat, a little bit of a provision, a little bit of a constraint, and that's how you should think of provisions. Okay, so now let's put this FIFO to use. So I have this combinational blob F. And what I want to do is I want to evaluate it repeatedly. So I have input values, a FIFO sitting here, constantly values are coming in. I pick the first one, apply function F, and put it in the output FIFO. That's the kind of system I want to build, where I'm trying to stream this function F through it. Very useful function, you will use it very often, this construct. And it's fairly straightforward to write. So I write a rule here. I've named it stream, this rule. And now tell me, what is this condition saying? What is this if predicate? Under what condition this computation can go on? Yes?
If there is an input, then there's room for output.
Exactly. That there must be something in the input queue and there must be some space in the output queue. It should not be full at that point. So we can write down these tests. If in queue not empty and if output queue not full, then what do? You take the first element of the input queue, apply function F to it, put it through this combinational circuit, and you enqueue it in the output queue. And at the same time you say dequeue it from the input queue. So that's why you have inqueue.dequeue, because you have consumed that value at this point. Everybody understands the importance of these checks, right? I won't get into the details of it, but you may want to go home and think about the code and see what will happen if you did not perform this check. You will discover it will not behave like a FIFO. You will just go and overwrite whatever you want in this. Many values may get lost if that happens. Okay. And syntax wise, people, including me, gets confused between single versus double ampersand, and this is a Boolean AND operation as opposed to bitwise AND operation. Okay. Now I come to a very important concept here, which is guarded interfaces. So you have already seen that we are always checking, is the FIFO full, is the FIFO not full, right? Is the GCD ready, is the result ready, is the result not busy, etc. We are always performing these checks. Maybe we can make the life of programming somewhat easier by performing these checks internally as opposed to performing them externally. And when we do that, we call them guarded interfaces. So every method has a guard. There is an abstract notion that a method can be applied only when it's ready. And I will show these guards usually using green lines in the thing. So it's a circuit light coming on saying, please press the red button only if it's ready. Otherwise, the system won't function. And actually, we don't rely on the programmer. Compiler will take care of all this for you. But every method has a ready wire, right? And then a value returned by a method is meaningful only if the ready signal says true. See, I could have read anything anytime I want, right? Because read methods, but that value is not meaningful. That value is meaningful only when the associated green line says I'm ready. Okay, so that's the idea of for value methods, right? For every action method, it says, please do not enable me unless I say I'm ready. Because otherwise, confusion will arise. Things will go wrong in this. Okay? And same thing is true for action value method, which I haven't shown in this case because we don't have it. So when I show you the interface of this new FIFO, now I don't have these flags explicitly, not busy, not full. They have become implicit. They are encoded in these green lines that are coming out of your circuit over there. Okay, so has everybody understood that every method is going to have the notion of readiness, which is indicated by the green line being true, right? There is a signal coming out saying, yes, I'm ready, you can read my value. Or if you want, you can perform this action right now. Now, all these things, notice enable, ready, etc., do not appear in the interface because it's implicit. Every method is going to have a ready line coming out. Every action method and every action value method is going to have a red line going in, enable signal going into it. So this is the implementation I had given you earlier for the FIFO, and now I want to guard it. I want to introduce guards in this, right? So notice this green. What is this green saying over there? Somebody argue it out for me. What is this? How will you read this? So you will say, you can perform this NQ action only if it's not full, right? Only if it says not V. Now based on this, you can imagine what the guards of the other, the syntax stuff, okay, all right. For you to be able to read it or DQ it, there must have been some value in it. So the guard is V must be true for these things. So this is the internal view of it. We are saying under what condition it's okay to use this method. And how is this condition reflected externally? Whatever expression I'm writing in green, its value is going to be connected to that green line that you saw coming out of this. Okay, so that's the idea of guards. You have taken in the computation inside, right? Guard expressions is what is connected to the ready wire of a method. So I have just moved the work a little bit. I don't want to perform these checks outside, and now let's see what is the advantage of it. So let's try to write that streaming function again, but let's assume we have guarded interfaces. If we have guarded interfaces, then I don't need this. I don't need to write this. I just say pick something from here, put it over there. Why don't I have to write guards anymore? Explicitly, why don't I have to test it?
Because it won't do anything if it hits the guard.
If the guard is not ready, right, this code can't be executed. And you will pretty soon forget the details of this because this is all going to be taken care of by the compiler. You have already done your job when you wrote that code implementation and you wrote something in green. You wrote the guard over there, right? That guard will automatically be lifted out and the compiler will go and check are all the guards of the methods that are being called, are they all ready? If they are all ready, then it will call it, otherwise it won't. Otherwise it cannot. So these are called implicit guards. Previously we were checking it and now it's implicitly being done over here. Implicit guards of the methods are sufficient because the rule can execute only if the guards of all its methods are true. Yep.
So is there any way to check whether or not the action is actually happening versus not happening? Like what if you expect something to happen, but it turns out that the guard is false? Is there a way to check?
So this is, you will get a good taste of that when you debug your labs. So you'll say, why is it not firing, right? Right, so that's we'll show you some debugging tricks for that, but you can read all the signals you want, but it's enforced very correctly, right? So when it says it's not ready, that means some guard is false at that point. Yes?
So in a rule it just stops. If you have like a normal block of code and it calls a function, but the function is guarded, does the code just stop executing until the guard is gone?
Say it again.
If you have a code which calls a function, but the function is being guarded, will the code just block it and not execute until the guard is lifted?
Interesting question. So first of all, until now, whenever we use the word function, we always mean combinational circuits, right? So combinational circuits for us just have a propagation delay. I mean, there is no notion of a combinational circuit being busy, right? You just put something in. So when we talk of busy, what we mean is that there was some state based on which I was computing, and it was taking several steps. And in the meantime, if you go and change that state, input state, then I'll be in trouble, right? So if you're calling functions and they're combinational functions, from your point of view, they're all instantaneous, right? There is no notion of time in between. Yes?
I also think it's like important to like say that you'll get in trouble if you think about this as code that is executing. Like we're still generating hardware that is always physically present, always doing something. What these guards are is like extra wires that will tell your circuit to like ignore the results of this, or don't actually, you know, set the enable wire to this register or things like that. But if you think about this as like, these aren't programs, these are descriptions of hardware. And sometimes
this is a very, thanks for reminding me of this. And you will get a full dose of it in the next lecture, right? Because we will show you exactly what hardware is being generated. But I keep using software analogs, a function is being called, but really it's all there all the time, right? In this, there is a circuit corresponding to it. Now let's quickly look at GCD. So this is the one I showed you without guards, and with guards, and this was the interface. And when I do it with guards, it doesn't have this busy and ready signals because they are encoded in these green signals. And your interface simply becomes just cross out these methods, because I don't have to worry about guards anymore. And let's see how this is helpful. So this was my GCD with guards, without guards, and now I have to introduce guards. So tell me, when can start method execute? When can start method execute?
when busy flag is false.
Right? So here you're seeing if the busy flag is false, then it can execute. That's the guard. That's the thing that is guarding it. It'll become the green signal going out. And similarly, what about the next one? Get result. When x is 0, right? Except that, yeah, there's a little bit of a nuance in that, because x is 0 to start out with. So we don't want to treat that as an answer. So we say, well, you must be busy, and then if x is 0, that means you have finished the computation. Okay, so that's the guard for this case. And rules can also have guards. So if you write it, you can have P over there in this case. Okay. A rule, just like a method, can execute only if its guard is true. So until now you haven't seen any rules with guards. But I just wanted to show you that the rule I had written so far, if I wanted, I could have written it as 2 rules with guards. Right? So the first rule is what? It's describing what happens when there is a subtraction to be done. And the second rule is describing what happens when swapping is to be done. And these 2 cases are mutually exclusive. So I have put that conditional I used to have as part of guards. This is often called rule splitting. It doesn't matter whether you write it like this or you write it the other way. Whichever suits your fancy. When it matters, we'll discuss that again. But semantically, they're the same thing. Right, so I had shown you how to stream a function. But now I have this module, which is, it takes time. It's not instantaneous. But I want the same idea. I want to keep feeding it values and I want to keep getting answers, from it. How will I build such a system? So very first thing I'll do is I'll create three things. I create two queues, in queue and out queue. And I instantiate by GCD, because I know how to make a GCD. So I've instantiated it, and now I have to write two rules to glue them together. One rule that will pick things from the in queue and put them into the start function. Another rule that will take things out from the get result and put them in the out queue. So when you do that, now you have a full system, and the code for this is really almost trivial to write, right? So you can see it. Oh, there's a minor complication that the value in the FIFO is really a pair, right? I'm representing it as an array of two elements, right? So each element of the FIFO has two things in it, 0 and 1, so that's what I have here. I take them out and I put them in the start. No checking being done. But if you really wanted to think about it, is there a checking being performed? What compiler will insert in this automatically is what is called implicit guards. If you wanted to make them explicit, that's what they will look like. So what does this guard tell you? What is the first line of the guard telling you? Anyone? It's saying that input queue first is ready and input queue DQ is ready, which is really just saying input queue has something in it, right? Input queue is not empty. And the second one is saying that output queue has some space in it. See, it's saving you a lot that you didn't have to write all this stuff. It's avoiding all kinds of errors you would have made if you had to do it explicitly. And similarly, there is an implicit guard over here. So even though we started out without guarded interfaces, once you learn about guarded interface, I guarantee you're going to love them, because it cuts down your burden and avoids lots and lots of mistakes of the This is a wonderful example, and I don't have time to finish it. We'll continue with this next time. Okay. Goodbye.